Hello everyone, this is Professor Iris Miano. I have a little lecture video for you here for my Math 2+2C audience. So we're going to be covering technically four algebra review sections. This PowerPoint that I'm going to go through first is just the first couple of sections regarding constants and variables and of course translating verbal expressions. You have lecture notes that coincide with these sections and they're fill in the blank style, so definitely if you could have those available so you can fill in the blank, or at least blank pieces of paper so you can write notes along the way and solve the problems with me as we go. All right, let's hit it. We're going to start off our conversation with order of operations because it'll do us no good to talk about simplifying expressions, translating, all of those things that are coming our way, monomials, polynomials, which is the next PowerPoint that I'm going to open up and show you, unless we are sure that we know the order of operations agreement. So you may have heard of PEMDAS in the past. PEMDAS is okay. If you're into PEMDAS and you use it successfully, it's fine. Personally, I'm not a fan. So I'm going to give you a new acronym that is shorter and hopefully a little bit more straightforward about the caveat that I feel like a straight up explanation of PEMDAS doesn't always cover very well. So here it is. Yes, I think PEMDAS is a little misleading. Let's talk GEMA, everybody. So GEMA is the acronym, and I like to set it up vertically as you can see here. What do these letters mean? Well, the G stands for grouping symbols, and I have several of them shown here. Parentheses, brackets, braces, absolute value symbol, and this last one right here, which hopefully you could see with my cursor, is a division bar. I know it kind of looks like a subtraction symbol, but the intention here that I'm trying to illustrate with this list of grouping symbols is to call it the division bar. Okay, so all of those can be considered grouping symbols, and I'll show you examples in which we would use them as the first item that we're considering in simplifying expressions according to the order of operations. Now the E in GEMA is the same as the E in PEMDAS, and it stands for exponent. So after you've addressed all of the grouping symbols, and by that addressing them I mean simplifying everything inside of them, you'll want to move on to simplifying all instances of exponents. After that, you will go through what is left and look for any instances of multiplication or division. And you're going to evaluate whichever one comes first from left to right. Now, PEMDAS, on the other hand, has the M before the D, and so some folks think that that means that multiplication always needs to be simplified before division, but that's not the case. What's actually happening here in the order of operations agreement is that we have multiplication and division are on the same level in the hierarchy. So you look for what you have, and you say, you're like scanning from left to right, and you're like, oh, there's a division here and it's happening before multiplication. Do that division first. I know it's a little bit counterintuitive if you've been, messed up in the past by PEMDAS. So hopefully we're going to do some healing from our PEMDAS trauma and have a good time simplifying expressions using GEMA. Now, A, as you could probably guess, is very much similarly defined as M was in GEMA. A stands for addition or subtraction because just like the M in GEMA, it stands for multiplication or division, and they're at the same level. Same for A. It represents both addition or subtraction, whichever comes first from left to right. Okay, so let's go ahead and implement the order of operations rule with some examples, okay? And I'll probably go through these relatively quickly. They're arithmetic. There's no variables just yet. We just want to make sure that we're feeling good about the order of operations agreement in a relatively simple setting. So with example A here, I've got 3 plus 2 times 4 to the second power. Notice there's no grouping symbols, so we can skip the G, but we're going to go definitely for the exponent being simplified there. So notice in my next step here, I'm writing down the entire expression over again after an equal sign with only one item, the next item that's able to be simplified. That's the only thing that's changed. Everything else gets copied down that hasn't been addressed yet. And by that I mean the addition and the multiplication. Now among those two, operations that are left after that first exponent was addressed, which of the two is higher up in the order of operations process? Well, you would definitely do the multiplication before the addition, so that's what we'll do next in the next step. And then, of course, lastly, we have the addition, which yields a final answer of 35, which I have boxed up in purple. Cool. Now for part B, notice that there's only two operations going on here. There's no grouping symbols, so skip G. There's no exponents, so skip E. But we want to address the multiplication and division that is happening here, you know, in the reverse order that I mentioned. So as you scan from left to right, notice the division is happening first. Do not let PEMDAS twist you up anymore. You know, because of GMA, that the division should happen first. So let's go ahead and divide the 7 out of the 28 and get 4, and then multiply that resulting 4 by the 2 and get 8 as our final answer. Okay, now in part C, notice that there's a couple of instances of grouping symbols. There's parentheses on the inside, some brackets on the outside. So just, you know, like you've been probably told in the past, with when multiple grouping symbols are present in an expression you're trying to simplify, always working from the inside and then go out. So we're going to start with the parentheses, and we're going to add the 6 and the 3 inside the parentheses to get 9. Then notice that the parentheses at this point, in this stage of our simplification, don't hold any operations inside of them. They're no longer acting as a grouping symbol, you guys. They're actually acting as an implied multiplication with the 2 that's sitting next to it. So now it's we can move outside of the parentheses and recognize the grouping symbol of the brackets next, and ask ourselves what kind of operations are happening inside the brackets, because there's 2 of them and we need to figure out which one is going to be the next one that we tackle. It's definitely the multiplication between the 2 and the 9, and then we'll subtract off that other 9 in a separate step. So here is me addressing the multiplication. 2 times 9 gives me 18. Let's subtract the 9 inside the bracket. That bracket now is acting as implied multiplication with the 8 that's left out in front, and we get a final answer of 72. Great. Okay, one more example in this set. Notice that we have fractions everywhere, everyone's favorite, I'm sure. Yes, and we have 2 operations only to deal with, multiplication versus subtraction. Which one will we do first? We'll do the multiplication. But notice that there is an instance in which diagonal across the way neighbors are sharing a common factor. So it might be nice to kind of cancel out those common factors first. And this is how I represent that generally. Okay, so I cancel out the common factor of 3, which is essentially dividing out a 3 from both the 9 and the 3 in the numerator of the left-hand fraction and denominator of the right-hand fraction, respectively. And those remaining factors get multiplied, numerators to numerators, denominators to denominators, and I will have that multiplication turn into a 3/5. Okay? Now you can multiply first and, you know, ask questions later. And by ask questions, I mean reduce later. But I think it's less work to do that, what do you call it? Canceling out the common factor thing first. Now we need to subtract, but check this out. Those fractions do not have a common denominator, so we're going to have to, you know, do all the things that are associated with that, LCD, all that biz, which we will definitely review in this class as much as you guys need. Just let me know. So I noticed that the LCD here is 15. How do I know that? Well, the denominators of 5 and 3 are both prime numbers, so whenever your denominators are all prime, you just multiply them together to get the LCD. And so this is how I'll do it. I'll bust out some what I call fun ones. Look at that, which are just fractions whose value is 1 but have a fun representation. 3/3 and 5/5 are the ones that I'm referring to here. We'll use them to get the common denominator happening of 15. Then we can subtract, double check to make sure that it can't be simplified. This one cannot, the 4/15, which I boxed up as my final answer, so I am good to go. Okay, let's move on to evaluating some algebraic expressions. So when this happens, you are going to be substituting some numbers for variables and simplifying. So what is a variable? Well, it's a English language letter, or sometimes it's a Greek letter. That is representing some unknown value. Now, when it is set equal to a number and you're asked to evaluate an expression using those particular values, you plug in those values. So here we go. The expression in question was 2y minus x, so it's said in the prompt to evaluate this expression when x equals 1, so plug in a 1 in the x position, and then y equals 4. So again, plug in a 4 in the y position. And I like to, when I plug in numbers, put them into parentheses, even though it might not be necessary. Like for instance, you could just have this one without parentheses, and that's perfectly fine. Parentheses kind of necessary for the y though, because you need that implied multiplication to be there. Or I guess you could use a raised dot, but you want to be careful, especially when you plug in negative numbers. Those have got to be done with parentheses, I would say, like emphatically. Okay, now what do? We multiply, and then we subtract according to order of operations. That's our final answer, 7 this time. Okay, let's do a couple of more examples very quickly. Plug in those values, which in this case will be x equals 1, y equals 5, with the different expression that's just riddled with fractions. Luckily the denominators match though, so we should be able to add those fractions straight away and get 6 over 4, but please do check to see if your final answer or if the answer that you currently have, if it's a fraction, is reducible, and if it is reducible, please do reduce it. So 6/4 definitely reduces to 3/2 when you recognize that both numerator and denominator have a common factor of 2 that can be divided out. So make sure you do that. All right, for the B example, remember, plug them in with parentheses just to be safe. We have exponents, so evaluate those right away, and then subtract. Bob's your uncle. Okay, that's that for that particular example. Okay, moving on. We're going to determine whether a number is a solution of an equation, and that's basically just plug in the number and simplify. And if you get the same value on both sides of the equation, then you have a solution. And if you don't get the same number on both sides of the equation, then whatever the number is that you were trying to see if it was the solution, it is not. Okay? Cool. So there's some places for you to fill in the blanks, I think, for that on your lecture notes. So, you know, if you printed out the lecture notes or otherwise have them on a tablet or something, then you can fill those in. Okay, so let's go ahead and do a quick example. Let's decide whether 3 is a solution of 5x minus 10 equals x plus 2. So, you know, plug it in. Notice that I have a little question mark above my equal sign. That's not standard notation. I just like to put that in there when I'm not sure if the two sides are equal. I'm investigating this. So we'll simplify, and then notice, look at this. We have the same value on both sides of this equal sign. So it is indeed a solution, right? And by it, of course, I mean the value of 3 that we plugged into the equation. Okay, moving on. Let's talk translating, okay? This is turning phrases into algebraic expressions and sentences, into statements, equations, or inequalities, right? So depending on the phrasing, we want to be able to turn some English language stuff into mathematical stuff. It's translating just like you would when you speak different languages. Mathematics is a language. I know that's such a silly cliche thing to say out loud. Like you've heard it your whole life so many times. I'm sure you're like rolling your eyes at me. I get it. And I don't blame you, but it's true. All right, let's go ahead and talk about a very basic example just to start off with. And let's see. Oh, whoops. I'm getting ahead of myself here. So the example states we want to write an algebraic expression that represents each phrase. Let x represent the unknown number. So if we're trying to represent the product of a number and 5, a number, that phrasing is supposed to be the x according to the preliminary instruction, right? So product, what does that refer to? So it's your job to know what word matches up with which operation or symbol, okay? And in this case, product is talking about multiplication between some unknown number, call it x, and 5. So we can represent that with 5x simply, okay? And that's as easy as it gets to start with, and then it gets more complicated the more complex your English language statements or sentences are. So we'll just cross those bridges when we get to them. Okay, now at this point in your lecture notes, you have a list of keywords and phrases that it's a non-exhaustive list, okay? There's certainly more keywords and phrases that allude to the 4 basic operations and equality, but definitely that's a good reference to start off with. And those will help us get through at least these 4 examples together. So let's go ahead and do the same thing. We're going to write an algebraic expression representing each phrase, and anytime we see the phrasing a number, that'll be the unknown number that we represent by x. Okay, so a number added to 7. Added is addition, right? That one's kind of a forehead slapper, right? You're like, duh. Okay, but there we go. And there's actually 2 options for translating this one because addition is commutative, right? So if you don't know what I'm talking about, let's definitely talk about properties of operations. Addition definitely has commutativity, which means you can add things in whatever order you want, backwards or forwards. X plus 7, 7 plus x, it's the same all day long. Okay, 3 times a number. Now that a number phrasing is alluding to an x, and times is talking about multiplication. So we could represent by a 3x. Could you also represent it by an x times 3 with like the times being represented by a raised dot? Sure, but that's not very conventional. Okay, and it's not very concise either. And one thing that mathematicians strive for with their representation is being as concise as possible. Okay, part C, a number subtracted from 8. Ooh, careful with that one because subtraction is not commutative. So the order in which you put the items in a subtraction translated statement is very important. Subtracted from 8. So that means 8 is in the what we call the minuend position. That's the first position if it's represented horizontally from left to right, and the subtrahend position is the item that's being subtracted off. So there's some really archaic terminology for you. Minuend is the item being subtracted from, and subtrahend is the item being subtracted off. There you go. Ooh, and here's a 2-parter for this one. Twice a number plus 1. Well, that'll be 2x to represent twice a number, and then the plus 1 happens outside of the multiplication. So I hope that was helpful, okay? Let's go ahead and do a few more that are more complex, okay? And of course there's going to be x representing the unknown number. Oh, and the thing that's special about these last 3 examples is that there's the word is or some other type of word that is translating equality, non-equality, or some inequality. Hint, hint, hint. That's what we have for parts A, B, and C respectively. All right. Reading A, it's the difference of 10 and a number is 18. All right. So that'll represent be represented as follows. The difference of represents subtraction. Sorry, I couldn't think of the word subtraction. And the order of the items is the same as it is in English versus mathematically translated. Okay, so there's one phrasing in particular with subtraction that's very tricky. So that'll come up in, I think, your homework, and we could talk about it in class just to make sure everyone's on board with that one. And then the word is comes up. Now that translates to the equal sign here, and then of course the 18 just gets slapped at the end. Okay, so for part B, we're trying to translate twice a number decreased by 1 is not equal to 99. Oops, and I accidentally pressed go to show the translated version of that there. And yes, notice we have a not equal to symbol there. That's just the equal sign with a slash through it. And there are instances in which it'll be appropriate for you to represent that. Now here for this last one, we have the quotient of 8 and a number. So the quotient is definitely alluding to division, and then is greater than. In this context, we are talking about an inequality symbol. So that's what how we'll represent it here. And look, I have 2 different ways to represent this. The fraction representation of the quotient is definitely more conventional. This old-timey symbol, like of the horizontal way to represent division, is definitely phasing its way out of your mathematical career personally. So it's there, but definitely go for this representation. Is just more appropriate. Okay, I believe that concludes. Okay, the 1.8 in 1.1. Now let's talk about monomials, polynomials, addition, subtraction of polynomials. That's my next PowerPoint, which I'm going to call up right there. And this is a separate document of lecture notes. All right, and here we go with those. Definitely pause the video at any point if you just like need a break from what I'm doing. Watch the videos over and over again. That's why I have lecture videos in general. So you have those options, and to watch them whenever you want. Here we go. Let's start with vocabulary here. Now, I definitely have places for you to write down these definitions because I think it's important for you guys to make sure that we're all on the same page on knowing what these the definition of these words is. So a term in a mathematical context is a number or the product of a number and variables raised to powers. Okay, so I want you guys to write that down or otherwise internalize the definition of this term, I guess. Okay, then there's a coefficient that I want you guys to know about, and it's defined as the numerical factor of a term, okay? And a constant is a term that is just a single number having no variable part, okay? So if you need to pause the video at this point to write down these definitions, by all means do so. But we want to move on to the definition of a polynomial. It is, and I believe this one is already written in your lecture notes, so you don't need to write this down. A polynomial in X is a finite set of terms of the form ax to the n power, where a is a real number, the coefficient, and n is a whole number. That's the exponent on the variable part of the term, okay? So here is an example of a polynomial. So notice that it's a finite set of terms. There are 1, 2, 3, 4 terms. Terms are always separated by addition and subtraction, okay? The first term is 4x to the 4th power. The last term is 12, and then there's 2 terms in between, right? A, which is the coefficient of each term. The coefficient of the first term is 4. The coefficient of the second term is technically -7. Yes, when you have a subtracted off term, technically that subtraction symbol is the sign of the coefficient of that term. So you can get a little confusing there. The coefficient of the third term here is 5, and the last term is a constant term. Notice there's no variable part. Okay, so hopefully that's all very clear. How the definition of the terminology that's been established so far in this section fits in with the items that you see in the polynomial in this example. Now, let's go ahead and define types of polynomials. This is, I think, a fill in the blank in your lecture notes. A monomial is a polynomial with exactly one term, mono meaning one. Binomial is a polynomial with actually exactly 2 terms, bi meaning 2. A trinomial, a polynomial with exactly 3 terms. And if a polynomial has more than 3 terms, it's just usually known generically as a polynomial. Okay, cool. Sweet. Moving on. The degree of a term, that's the sum of the exponents on the variables contained in a term. That is something that I want you to distinguish between what the degree of a term is versus the degree of a polynomial. So the degree of the polynomial will be the highest degree term, or the highest degree that you see among all of the terms. Or sorry, what does it say here? The greatest degree of any term in the polynomial. Sure, it's the highest one that you see. Okay, great. Let's test our ability to internalize all of the terminology that you've just been presented with and find the degree of each term. Okay, so notice in part A, we are given, in each of these examples here, it's a monomial, or just like a single term in maybe a polynomial that's not shown, okay? But what would be the degree of the term here? Well, for this one, there's only one variable part, and it's raised to the 3rd power, so the degree is 3. But for part B, notice that there's two different separate variables, right? And they're each raised to the 2nd power. So the degree is going to be their sum, the sum of the exponents. By that I mean the 2 and the 2 exponents that you see on the x and the y. I'm talking about example B here. The sum of those is going to be 4. Now, for part C, notice that there's no exponent explicitly given on this x variable, but it's hidden, it's like invisible, and the exponent on the x is a 1, so the degree of that term is 1, okay? Now, For part D, notice that there's 1, 2, 3 different variables in this term, and the exponents are an invisible 1 for the x, a 2 for the y, and a 4 for the z. Add all 3 of those exponents together, even the hidden one, and you should get what? 7 is the degree of this term. Now, notice that there's no variable part for part E example, so what do you think the degree would be there? Well, if there's no variable part, then technically the variable part, you could argue, has degree 0, so, or an exponent of 0, so the degree, therefore, for any constant term is 0, okay? Great. Now, let's have a different set of examples, and let's find the degree of each polynomial, tell whether the polynomial is monomial, binomial, trinomial, or none of these, which would just generically be called a polynomial. Or, use the phrasing none of these would be fine. Okay, let's start with example F. Now notice that it is has a variable part in it, so it's definitely a non-zero degree, and it looks like the highest degree will be a 1. So this is a first degree polynomial, okay? Its type would be, well, how many terms does it have? It has 2 terms, so it would be called a binomial. Great. Moving on to example G, look at all of the different individual terms and look at their individual degrees. This first term is degree 1, second term is degree 6, third term is degree 4, and the last term is degree 0. Now among all of these individual terms, which one has the highest degree? It's this second term, right? And its degree is 6, so therefore the degree of the polynomial is 6. Okay, it's the highest degree that you see among all the terms. Now what type is it? Well, how many terms do we have? 1, 2, 3, 4. It's more than 3, so we just call it a polynomial. In this case, because of the way the instructions were worded, we would just say none of these. But you would just generically call this a polynomial otherwise. Okay, example H, we have, looks like 3 terms, so that gives it away a little bit on the type, but I just want to look at the degree of each term. The first term in this polynomial is degree 2, the second term is degree 1, the last term is degree 0, or a constant term, so the highest degree is going to be degree 2, so that means that this entire polynomial is degree 2, and the type, because it's got 3 terms, we would call it a trinomial. All right? Very good. Okay, now, relatively quickly, let's consider this polynomial and take the term one at a time and talk about its numerical coefficient and its individual degree. So go ahead and fill out the chart that you have on your lecture notes area accordingly, or draw yourself a chart if you're not printing out the lecture notes, and write down all the individual terms there, and have the sign or subtraction operation come along for the ride, because that's still part of the term as well, okay? Now, what's going to be the numerical coefficient for each term? Well, for this first term, it's just going to be that -3 part. For the second term, it'll be the 4. For the third term, it'll be the -2. Yep, sign comes along for the ride. For this fourth term, it's got an invisible coefficient of 1, right? Okay, and then, yes, we wouldn't call it a coefficient for this last term, but, it's a constant term, but technically it does have a coefficient of, itself, basically. All right? So hopefully everyone's got that down and it's understandable. Now it's the degree of each term. Now remember, the degree of a single term is going to be the sum of all the exponents for the individual terms. So for this first one, it'll be a 4, and the second one it'll be 2, if I'm not mistaken, because the A has a 1 exponent and the B has a 1 exponent, not shown. And then it'll also be a degree of 2 for this third term, a degree of 1 here, a degree of 0 for any constant term. So we should have the following values here. Okay? Let me know if you have any questions about this when we come into class. Vocabulary, yes. Okay, so we need to nail down some more vocabulary in order to be able to add and subtract polynomials. That's our next term, or our next move, or a move that's coming up pretty soon in the lecture notes. Like terms are terms that contain exactly the same variables raised to exactly the same powers. So, and only like terms can be combined, so that's why we care about learning about this phrase, like terms, okay? Let's do some quick examples in which we simplify each individual polynomial by combining like terms, and then we'll finish things off with adding some polynomials and subtracting polynomials. So we're almost done here, folks. Bear with me. Let's do these kind of rapid fire. Now notice for the first example m, it's only a binomial, and both of the terms happen to be like terms. So let's go ahead and just add their coefficients together, right? So we see that they're like terms because they're exactly the same variables raised to the same power. It's just single factors of y. And so we just add the coefficients of -6 and 8 together. We'll get 2y. Okay, now for example n, we have two different sets of like terms. We have y² terms and we have constant terms, which are being shown lit up in red and green respectively. So gather them up and combine them according to adding their coefficients together or simply the constant terms together, and you should get the following final answer. Okay, now for example O, we have two like terms, but do note that that second term, x to the third power, technically has a coefficient of 1. So that's how we're going to get a final answer of 8x to the third for example O. Example P, it looks like we have only one set of terms that are like terms, and then the x² term and the subtracted off 15 are kind of odd man out. They don't have any other terms to be combined with, so we're actually only going to combine the -6x with the -x, or in order to ultimately get a subtracted off 7x. And that'll do it. That's the extent of the combining like terms that we can do for example P. That's your final answer. Now for example Q, we got a little bit of a tricky thing going on there. Do you guys see the tricky thing? Notice that the first and third terms are technically like terms, right? Because multiplication is commutative. AB is actually the same as BA. So we can highlight those as like terms, even though they don't look exactly the same from the get-go. So this is a little bit of trickery that you might be confronted with. So I want to give you guys the hint in recognizing the commutativity of multiplication. Okay, so we can combine those like terms and we'll get 10 ABs. And yes, I'm calling it AB rather than BA because when you have multiple variables listed in a single term, it is conventional to list them in alphabetical order. So I opted for the AB in my simplified form rather than BA. All right, example R, whoo doggies, what do we have here? We have, it looks like two separate sets of, we have actually three separate sets of like terms, because recognize that just like in example Q, we have x² y² being equivalent in term as y² x², right? Just switch them around. Multiplication is commutative all day long. So now we can combine like terms there. And yes, I'm sticking with the x² y² ordering of the variable parts in the red, like terms, the ones that I've colored red, just because, like I said, ordering variables in alphabetical order within a single term is conventional. It's like the thing that we usually do. Okay, great. And so now that we have combined like terms successfully, let's go ahead and add some polynomials, which is basically just combining like terms. Okay, so we have two examples here. Oh, sorry that this got cut off in a little bit of a weird way. Let's see how that goes down when we move forward with this. Okay, let's start with example S, all right? We're just going to add. So really, you can just kind of drop the parentheses at this point. Recognize that this first term in the second polynomial is actually, you could just re-represent this as subtraction. So there we go. I'm going to go ahead and drop the parentheses all the way by the second step, and then just look for your like terms. I have them highlighted in green and blue respectively, okay? And then add coefficients together to combine like terms, and that's as far as you can simplify. So that is example S for you. Now example T, it looks like we are, oh, goodness gracious, it looks like I am gonna have to, just a second. Let me try and fix this on the fly here for you. Sorry for the weird technical issue. So yeah, when you are adding them together, you just put a plus sign between the two, polynomials when they're given to you in this way. And then in this next step, notice which ones are like terms. There's x to the third power terms, there's x squared terms, and there's constant terms. There is an x to the fourth power term, but there's no other one like it, so it's not going to get combined with anything. Okay, now in the next thing that I want to show you, look at this. Oh goodness, that got a little bit carried away, but you guys can see that now. Okay, so there we go. We have x to the third terms. Yeah, everything has been combined here, so that'll give us our final answer on example T. Okay, we have a few more other examples that we want to talk about subtracting polynomials. Let me go ahead and put this back in the slideshow feature. When you subtract two polynomials, you really just need to change the signs of the terms of the polynomial that's being subtracted off, and then you combine like terms. Or I say add, but yes, combine like terms is technically the way you want to describe that. Okay, so here's our first example. We've got a polynomial 4x to the third minus 10x squared plus 1, and then we're subtracting off this other polynomial of negative 4x to the third plus x squared minus 11. So subtracting this polynomial means distribute this negative sign, basically. So you want to change the sign and operation of all of the terms inside of this subtrahend polynomial. And by subtrahend, like I said earlier, that just means the polynomial that I'm subtracting off. So here is the result of changing all the signs in the second polynomial, the one being subtracted. Here's me recognizing like terms, they're color-coded, and here is me combining like terms. And there you have it. That's example U for you. All right. I have one more example V that I wanted to do for you. It's a little bit more complex, but it's the same principle. We want to start by distributing this negative sign over every single term in the subtrahend polynomial, the one that's being subtracted off. And here is what it'll look like once you change the sign and operation of the polynomial being subtracted. Then you want to recognize like terms. Here they are color-coded. Okay, now notice that a couple of the terms are not color-coded. They do not have a partner in which they can combine with, and that's okay. They're just going to come along for the ride. Okay, here is me combining like terms, and that'll be our final answer there. Okay, I know I just clicked forward and you saw a slide that has nothing to do with you guys. Please do ignore it. We are done with this lecture video, and you are fully ready to tackle the homework problems associated with these AR sections. Cool, cool, cool. That will do it. Thank you so much for your attention, and I'll see you again soon.